So, can you hear me? Okay, so let's start. Sorry about the mess up, and thanks him for fixing this. Okay, so let's continue. So this is the plan for today. I'll begin with some response to some queries, because after last lecture, some of you asked me some questions. So I want to respond to those queries. That takes probably 10 minutes or so. And then I'll give you two classical examples. Classical means both old, it is mathematics in old Greek times, and also it is the most famous theorems, the best theorems in mathematics. So I'll prove two theorems. After that, we are going to continue the line about sets. Right? Last time we talked about sets, and then today we are going to see more properties about finite sets. Especially, we will do some counting argument to count the numbers in a collection. Okay, and then the last part is about functions and some property of functions. I believe the last part should be a revision. I will need it in the next topic, which is about infinity. So I want to make sure that we are at the same level. Okay, so these are the plans. Okay, so the first query was about how to write statements in symbols. I introduced some connectives. I also introduced some quantifiers. And then I give you some examples of mathematical statement, and then I turn the statement into symbolic form. And then there are probably in this particular example, the way I wrote something like this. This is sort of hybrid. It's halfway in between. So people get confused. So let's look at this example one more time, and hopefully I'll clarify your doubt. Okay, so the statement is a famous statement. It's a conjecture in mathematics, still open. It's called Goldbach conjecture. It says every even integer greater than 2 can be written or can be expressed as the sum of two primes. We talked about prime numbers last time, so I will not repeat. So last time I wrote something like this. The emphasis is, so there's a for all quantifier and there is a existential quantifier. But somehow this is not very clear, so let's do it again. Okay, so the question is, essentially, slightly more general question is this. How do we translate a sentence in the following form? So the first sentence is, every integer with certain property, let's call it P1. Every integer with property P1 has another property, has some other property, P2. For example, this Goldbach conjecture is in that form. It says every integer with some extra property. The extra property is an even integer, and also there are some more extra properties. So it's an even integer, and also it is greater than 2. So Goldbach conjecture is of this form. So it says every integer with some extra property has some other property. The other property says it can be expressed as sum of two primes, right? So essentially, we want to translate. So this is an example of the first sentence here, right? Well, if we can translate what happens for every integer, we are able to translate that is dual, right? So it's for example, some integer with property P1 has property P2, or there is integer with property P1 has property P2, right? So we let's figure out how to translate these two statements. Okay. Is it all right? Okay, let's try. So I want to translate every integer with property P1 has property P2. So the claim is this. For every integer, say x is integer, it translates into this. If x has property P1, then it has property P2. Right? So do you agree? Right? Every integer with this property, if it has this property, then it must have the other property. So this is the way of translating. Now, how about the other way? So how about the other sentence? Some integer with property P1 has property P2. It translates into, okay, there is some integer, right? There is an integer, x, which has P1, and also it has P2. So notice the red part, the translation are different. Do you agree? Okay. Do I have another example? Okay, so okay. So let's first let me try to give you a daily life example. Every girl in this classroom is smart. So it's every person with property who is a girl has a property is smart, right? So it says, right, every person here in the room, if she is a girl, then she is smart. This translation is correct, right? Okay, so now how about if I say some girl in the classroom is smart? It means there is a person here, she's a girl, and she's smart. So I'll find some weakness. Well, here she is. She's a girl and she's smart. So that's it takes time to get used to this, but it's quite reasonable. Okay, so now if you agree with this translation, the Goldbach conjecture you translate into this. For every integer, right, if it has property P1, that is, if n is even and n is bigger than 2, and then it has property P2, and then n is the sum of 2 primes. Okay, so far so good. Now let's open up this part. N is the sum of 2 primes. Actually, this is a compound statement. It says there are 2 prime numbers whose sum is n. Right? So n is a sum of 2 prime means you can find 2 prime numbers. If you add them up, it gives you n. So it is a form of this. Some integers with property P1 has property P2. Right? So it says they are integers, P1 and P2, and they are primes, and they sum up to n. Right? So this is the translation of this one. So if you want to get the full translation, you just cut and paste. Replace this part by this sentence. Is this okay? So I have to say that the translation is not unique. You may have different ways of writing things in an equivalent way. Right? And also, I have to say this is not a course on mathematical logic, and this is not a real mathematics course. So if how to say, if I'm not totally rigorous here and there, well, hopefully I can get away. If you are not satisfied, talk to me. I can make it super mathematical, but I guess that's not the point. Hopefully this clarifies some of the doubts. Okay. Now, I guess I want to skip of this. So I want to respond to the other query. The other query is, so last time I talked about Russell's paradox. And then what happens after paradox? What does it mean? What are the impact? So the story I was telling involved these two persons, right? Two famous philosopher or mathematician. So this is Frege. He is the father of analytic philosophy, and he is very important in the development of mathematical logic. And this is Bertrand Russell. We talk about his story, and he is an extremely smart guy, and he is everything. Right? He's a philosopher, mathematician, great writer, politician, activist, and so on and so forth. So okay. So what happened after the paradox? So Frege was trying to set up a logical foundation for mathematics, right? So Frege's hope was, if we have set theory, naive set theory, and we have logic, then everything else just go from there, right? And Russell says, no, the naive set theory has a contradiction. It's not safe. Okay, so what happened? So first, there is a way to get rid of the paradox. So first, people immediately after Russell's paradox, and people try to fix it, try to get rid of the paradox. Russell himself had some ideas. He used his type theory and so on and so forth. But the lessons people learn is not every collection can be called a set. Naive set theory somehow is too naive because any collection, any property will give you a set, right? So that's too naive. We cannot be so generous. So not every collection can be called a set. We must add some conditions. So only certain collections can be called a set. And those bad things we do not admit them into our system. So we must write down some conditions in the form of axioms. Only those collections which satisfy the axioms we allow them to be set. So in this way, more or less, we do it sort of in a cheating way. Right? We look at those problematic sets. We sort of say, no, you are not set anymore. Now, to be a set, I draw the line. You are not. You are outside the line. You are somewhere there. Okay, right. So in this way, we expel these problematic collections, like those Russell's collection. Right? Well, after that, it seems to be safe. Nobody found any other paradox to attack axiomatic set theory. So I don't know whether in future I'm going to mention this or not, but probably it's nice to know. So the typical axiom of set theory are called, in this shorthand, ZFC or ZFC. So Z stands for Zermelo. He's a German mathematician. Actually, there are documents says, actually he discovered the Russell's paradox even before Russell, but he didn't make it public. Franco is another logician. F for Franco. And C is not a person. C is the axiom choice, whatever it means. Okay. So which contains about 9 schemes of, it depends on how you write them. So the usual writing is probably 9. And scheme means sometimes the axioms are not a single axiom. It's a family of axioms of the same pattern. So we call it a scheme. So you have a collection of axioms Now, if you only admit collection satisfy these axioms to be set, and then you are safe, more or less. Okay. Now, but you may protest, right? Because originally, when we look at naive set theory, we thought it's safe. Right? Only Russell comes in and he says, look, here you have a problem. Maybe some of you are so smart, then you look at ZFC and immediately you discover something. Look, here you have a contradiction. Is it possible, right? So the question is CFC safe? Now I want to use the word consistent. This is a mathematical word for safe, for no contradiction. Right? So in mathematics, inconsistent means contradictory. Inconsistent is bad. And consistent means not contradictory, so it means good. Okay. So the question is ZFC is the axiom we use for set theory. Is it safe? Okay. So now then, actually in the 1930s, David Hilbert is maybe one of the greatest mathematicians. He wants to prove mathematics is safe. He is a leader of the mathematics, the first half of 20th century. So he wants to make sure that mathematical foundation is solid. So he has this Hilbert program. He wants to show mathematically that mathematics is safe. There's no contradiction. Right? And then comes another guy called Gödel. Gödel showed that Hilbert's program cannot be carried out as he proposed. You may find other ways, but what Hilbert proposed is impossible. Okay, so the story goes like this. So here, I remind you of the question. So is mathematics safe? Right? Does it contain paradox? Right? So the hope Hilbert has was we can prove. Let's try, right? Mathematics is very, very powerful. We can do lots of things, right? So can we prove using mathematics that mathematics is safe? There's no contradiction, right? Now, mathematics is a vague word, so let's try to make it more rigorous. So it turns out most of mathematics can be formulated using set theory. So it's almost true that the ZFC is mathematics. So the mathematics you learn in NUS after 4 years definitely can be done in ZFC. So ZFC would include all of these. Right? So let's assume ZFC is the rigorous version for mathematics. Otherwise, it's too vague. What is mathematics? The line is hard to draw. So let's try. Let's use ZFC to replace mathematics. So the question becomes, can ZFC prove its own consistency? Can ZFC show that itself is consistent? Right. So this is the question. Now, what Gödel did is, he has, in 1930s, he has two famous incompleteness theorems. This is one of them. So it says more or less, okay, I cannot make it fully mathematical. So there are some words are not well defined. Okay, so basically it says this: any reasonable formal system is like axiomatic system. I cannot explain using in the short time. So any reasonable formal system, reasonable means it's safe. There's no contradiction. And also it can say something. If you don't have any words, then you are safe, right? So, but the condition on the reasonable include that you have to include plus and times. You can do basic arithmetic, okay? So if you have an axiomatic system that includes part of the number theory, and then you cannot prove your own consistency. So in particular, let's assume CFC is consistent, and then he cannot prove his own consistency. So you cannot prove you are safe. Right? This is a, but then some people will say, oh, then mathematics is not good, right? You don't know whether it's safe or not, and maybe there's a contradiction, and how do we have confidence in you, right? So, but however, actually, there are lots of signs. We cannot formally prove it, but experience tells us it's quite safe. Okay, so this becomes philosophy. I cannot mathematically show you, but I'll try to give you some evidence. Okay, so actually last page I give you evidence saying, so far nobody find, no matter how smart they are, nobody find any more paradox. Right? Also, there is another kind of argument, indirectly show that it is safe. So usually, you look at well, I cannot show you that, but you look at the axioms in ZFC. Some axioms are very simple. Say union, the union of sets are sets. Something are very, very simple. Some of them are more complicated. So usually people would think that the complicated ones are bad. So we have to be cautious, right? If you have an axiom which is very, very complicated, how do you know it is safe? For example, axiom choice. It's for those who know what axiom choice are, what axiom choice is, it's a complicated axiom. Now maybe that axiom is not safe. Well, however, actually this is done by Gödel, the same Gödel. Gödel showed there are some kind relative consistency. So it says if ZF without axiom choice is safe, and then you add axiom choice, is still safe. So you don't need to worry about the problem brought by axiom choice. If originally you don't have any problem, and then you can say you can use axiom choice without any worry, right? So the same apply to some other axioms. So some other axioms looks very, very complicated, but somehow there's argument shows if the simpler ones are safe, then that complicated one is also safe. So therefore, people sort of shrinking the how to say, instead of looking at very, very complicated collection, somehow you can look at a relatively simple collection. And for the relatively simple collection, most people will believe it's safe. Right? There's a degree of confidence, right? For example, I'm talking about natural numbers. Usually you won't doubt the natural number will give you trouble. But if I talk about arbitrary subsets of natural numbers or some very, very abstract things, then you may have doubt. So there's a relative scale. So currently the mathematician is able to reduce the, how to say, so reduce the size of the problematic part. So most of people with a normal mind will not have doubt. The simple part is safe. Right? So there are some signs of safety. Okay. But however, we cannot prove it. So it's still it's like an experimental science. Maybe next day it become unsafe. Okay, now, oh my God. Okay. So now, so there are some interesting consequences. This is a famous theorem, so you can read lots of articles, lots of books about it. But I want to state two interesting consequences. One is, by Gödel's theorem, if a system claims he's consistent, he can show his own consistency, actually he's cheating. He is inconsistent. Right? Because Gödel's theorem says, if it's reasonable that you cannot prove his own consistency. If this guy is able to prove his own consistency, then he is cheating. This is an interesting consequence. So if somebody tells you, oh, I cannot prove I'm safe, yeah. So then actually he has a great chance to be safe. Now if you have somebody who tells you, oh, I'm consistent, then you have to be cautious. Most likely he's cheating. The other thing is the consequence of this incompleteness theorem says mathematics is inexhaustible. So there's no boundary. Right? If suppose you have one formal system which exhausts all possible mathematics, and then we don't need mathematicians. Right? So we just give these axioms to the machine, to computers. The computer just keep proving theorems, and that's all the theorem you can get. So mathematics is not like that because of the incompleteness phenomenon. You have a system, and then there's always something you cannot get. The typical example of something is the consistency of yourself. So you need to add something more in order to get the consistency of yourself. So that pushes you to go further. And this process never ends. So that's a wonderful fact about mathematics. So the mathematicians will always look for new axioms for mathematics. So mathematics will never stop. So okay. So that's the side remark on to respond some of the questions. If you have further questions or you have some other questions, please ask me. If I'm able to answer, I'll answer next time, like I did here. Okay, so now the next topic is the two beautiful theorems. So I want to start from this quote by British mathematician Hardy. So this is about proof by contradiction. So this reductio ad absurdum is a fancy way of saying proof by contradiction. It's probably Latin. So it says he says this proof by contradiction is one of a mathematician's finest weapons. It is a far finer gambit. Gambit is than any chess gambit. So the gambit in chess is a chess player may offer the sacrifice of a pawn or even a piece, but mathematicians offer the whole game, offer the game. So proof by contradiction says, okay, you take everything, right? So I suppose this is not true. You take it, and then somehow the mathematician in the end win the game, right? So this is his work. Now I want to so this quote actually is from a famous book by him. It's called A Mathematician's Apology. So he's defend his profession, mathematician. So in this book, there are lots of interesting quotes, right? So here I want to motivate, why do I choose two theorems to show you? I'm influenced by him. So he says this, okay. So I will state and prove two of the famous theorems of Greek mathematics. I guess typo. They are simple theorems, simple both in idea and in execution. But there is no doubt at all about their being theorems of the highest class. Okay, it's simple on one hand. On the other hand, is the highest class. So each is as fresh as and significant as when it was discovered. 2,000 years have not written a wrinkle on either of them. Finally, both the statements and the proofs can be mastered in an hour by any intelligent reader. But we are NUS students, so we can master it in 20 minutes or in 10 minutes. Right? So however slender his mathematical equipment. Okay, Okay, so we are going back to Greek times. So this is a famous painting by Raphael, right? So it's in the Vatican's. This is School of Athens. There are lots of famous Greek philosopher, mathematician here. And this is Plato. This is Aristotle. And the two theorems we are going to see, one is by, okay, so it's not exactly, but legend goes by, this is Pythagoras here, and Euclid. I'll show you a detailed graph, picture later. Okay, so here's Pythagoras. We know his theorem about right angle triangle, right? So, okay, so the first example I'm going to show you is the irrationality of square root 2. Okay, so the theorem says there exists no rational number whose square is 2. We talk about rational number, right? Rational number are the ratios of two integers. If a number cannot, an irrational number means it is not a rational number. It is not a ratio of two integers. So the statements about irrationality of square root 2 says there's no rational number whose square is 2. Okay? Now, in other words, this is irrational, and this is known by Pythagoras, and okay, so that's him. Okay. So in symbols, what you want to show is this. There's no rational number whose square is 2. Okay? So we know the rules of taking negation. I should change this to negation. Sorry, to the other negation. Okay. So this symbol is for negation. Okay. So we want to show the negation of this, but the negation of this statement is equivalent to, for all x in Q, for all rational number, the rational, okay, so the x square is not 2. Right? So our job is to rule out all possible rational numbers. And we look at rational numbers one by one, not square it, not 2, not 2, not 2. Yeah. Now, if you want to attack this directly, it's not easy. Right? We cannot check infinitely many rationals. So not easy to start. So then here comes proof by contradiction. Right? So let's try to prove by contradiction. We cannot start. So let's try the other way. Let's look at negation. So let's begin with the negation of the statement. Suppose it's not true, right? So suppose that there was such an x, which is a rational number. Let's see what happens. Okay? So at least we can start. We can start with a rational whose square is 2. Let's see what happens. Okay, so this x is a rational. We can write x as a quotient or a ratio of two integers, a and b. Okay? So this is the definition of rational number. So therefore, the a over b square is 2. Okay? Now you move things around, you get a square is 2 times b square. Okay? Now here, we need some intelligence. So the right-hand side is an even number. It's a multiple of 2. The conclusion is the left-hand side, of course, a squared is also even. Now, it takes a very small argument to get a is also even. Are you with me? So, if I know a squared is even, I can conclude a is even. The reason is sort of small proof of contradiction. If a is not even, it's odd, but the odd square is odd. So therefore, it's not the case. Anyway, so that I leave it to you to think of. It's fairly straightforward. So we are here. So if a squared is even, then a is even. Okay, so a is even. So a is a multiple of 2. Let's say a is 2m for some m. Okay. Now substitute a back to this by 2m. A is 2m. So 2m bracket square is 2 times b squared. So then you get this. And then you cancel off one copy of 2. you get 2 times m squared is b squared, right? Same thing. Now, the left-hand side is even, so right-hand side is b squared is even. And then this means b is even, right? But then something's wrong, because if both a and b are even, why don't we cancel them at the very beginning, right? So we should cancel those redundant factors, right? So that gives you a proof, actually. So are you with me for the discussion? The proof is almost is all there. The next slide is going to write it in a proper mathematical way. But the idea is just like this. Okay, so now here is a proof written in proper mathematical form. So suppose we want to show every rational square is not 2. Okay, so suppose a over b is a rational number, and here we add this condition, written in its lowest terms, meaning no common factors. Right? If you have common factor of 2, already cancelled. Okay. So written in its lowest terms, such that a over b squared is 2. And then we do our calculation. We move things around. It follows that a squared is 2b squared. Hence, a squared is even. Consequently, a is even. Right? So now, if a is even, you can write a, writing a equal 2m for a suitable integer m, we will have 2m squared is 2 times b squared. Right? That is 2 times m squared equal b squared. But this shows b must be even. Right? B also even, which contradicts to the fact a over b is in lowest term. Okay? Therefore, no such a over b exists. So this is one of the nicest theorem in the mathematics history. You'll probably have seen it, I don't know, in JC or even in elementary school. Okay. Now let's move on to the other one. So the other one is done by Euclid. So here the guy who is using a compass drawing some graph is supposedly Euclid. So we want to show that there are infinitely many prime numbers. Okay, I think we have seen the definition of prime numbers. So if a number can only divide by itself and 1, that's a prime. Right? In other words, you cannot factorize it in two, non-trivial ways. Okay, so this is known very early in his elements. He wrote a book in his elements there. Okay, again, let's try to see how the argument goes. So again, obviously, there's no obvious direct proof. How do I show there are infinitely primes? Can I give it to you in one shot? It's very, very difficult, right? So perhaps we should try to prove it. We should try to use proof by contradiction. Okay? So now, what is the negation of the statement? The claim is there are infinitely many primes. The negation will be there's only finitely many primes, right? Okay. So let's assume there are only finitely many primes. Let's write them out. So the first one is 2, I know. The second one is 3, and so on and so forth, until you hit the last one, which is, let's say, p sub t, right? So and let's see where we can go from here. So we have a complete list of all primes in the world. Okay, all here. Okay, so it certainly says that all integers bigger than pt are not primes, right? Because every prime is here. And after that, there's no more primes. Okay? But we know that every integer can be factorized or expressed as a product of primes. This part, again, you need some math. For any natural number, you can keep factorizing until you hit all the prime factors, until you cannot factorize. Right? That's a prime. So here you need some mathematical knowledge, but not too much. So therefore, any number bigger than this pt, the largest prime, should be divisible by one of the primes, right? Because every number can be factorized into a product primes. So therefore, every one of them has to be divisible by the one of the t many primes. Okay? But here, so here's some sparseness. You need to cook up a number which is not divisible by any one of these. Here's a trick, right? You multiply them together and plus 1. So none of these p's will divide this number, because if they, I claim, for example, this number is not a multiple of the first one. Because if this is the multiple of first one, and then you can write this number as k times p1, right? Now you move around, you get 1 is also a multiple of p1. So, but that's not possible. Let me see whether the next slide will, so next slide will have some detail. So I will, sorry, repeat the idea, and then we move on to the next slide. Okay, so we are trying to show there are infinite many primes. So we prove by contradiction. Suppose there are only finite many primes, which are p1, p2, up to pt. Okay, now the magic goes, we cook up a number by multiplying all these p1, p2, up to pt together, add 1. Okay, now we want to show that this one is not divisible by any of these. Therefore, we get a contradiction. Right? Okay, so here's the official proof. So suppose, to the contrary, that there are only a finite number of primes. Let these prime be p1, p2, pt for some t. Right? So now let n be this magic number, p1 times p2 times times pt plus 1. Okay. Now, certainly n is not a prime, because n is bigger than any one of these. So after pt, there's no more primes. So n is not a prime. So since it's bigger than all the supposed largest prime pt, so hence n is a product of primes. So let q be a prime number dividing n. Right? So there is a number dividing n. So then q must be one of the pj, because these guys are the only primes there. So q must be one of them. Okay? So let's say q is p sub r, just somewhere, p sub r for some r. So now this p sub r divide n, right? And also p sub r divide n minus 1, because n take away 1 is the product of these. And p sub r is somewhere here. So certainly p sub r divide this part. So therefore, p sub r will divide the difference of the two numbers, so which is n minus bracket n minus 1, which is 1. So p will divide 1, but that's not possible because p is a prime number. I'm sorry, I use a symbol, this stroke. This stroke means divide. Probably in the slides when I revise the slides, I will add some words saying this symbol means PR divides n. Or you can think of A is a multiple of PR. Okay. So therefore, the number of primes is infinite. Right? So that's another beautiful theorem by the Greeks. Now, for those of you who are very good at math, try this. just now we try to multiply the prime numbers together and add 1, right? So now let's try. So is it true that if you multiply the first few primes and add 1, okay, so this is the first prime, add 1, multiply first 2, add 1, multiply first 3, add 1, first 4, add 1, and so on and so forth. Is it true that they are all primes? Well, you don't need to give me the answer now, right? But whatever happens, it doesn't change our proof. Our proof does not need this fact. Okay, so think of it. If you have nothing to do, I know you are good. You know lots of things in math. Okay, so so that's the part about 2 nice examples on contradiction and on some general education of mathematics. Right? So I think the 2 theorems, if you never see it before, it's nice to know. Now, maybe I make one more remark. So this remark is about philosophy of math. So remember, in philosophy of math, we have the question that how do we learn mathematical knowledge? Now, suppose you didn't know square root 2 is irrational, right? Now you know it, right? Because we spent 5 minutes on it, so you know it. Now think of it, how do you know it? How do you learn this knowledge? It's not by experience. How do you know? Actually, you don't need my read the slides. I mean, if you think of it, actually you know it. Right? You can close your eyes, or it's not because of the screen, the light from screen enter your brain, or it's not because of the sound I say, but somehow it's just the reasoning. Now you know. So so mathematics is a very interesting knowledge. So in old days, Plato will say that you know it because in your previous life you know it, and then now you just remember it. But nobody, of course, now we believe science, right? We don't believe this. But it's different, right? In physics, you have to do some experiments, you have to see, you have to observe, and then you know. But for mathematics, it seems you just think. You don't. There's nothing from outside, but somehow you get some knowledge. Anyway, so this is for you to think of. Okay, so let's take a 3 minutes break, and then after that we come back to a new topic about sets. Okay, so let's continue. It seems that I'm telling you something you know very well already. So anyway, so the remaining part probably is also the same situation. Okay, so let me try to speed up. Okay, so we are going to do some counting argument. So today is some very, very simple counting. Next time we'll see slightly more different, more complicated counting. Okay, so remember we were talking about set last time. So the size of a set, let's assume the set is finite for a moment, denoted by the absolute value of this set A is the number of distinct elements in A. Right? For example, if you have this set, there are 3 elements. So the 2 bar of this set is 3. Right? Now suppose you have integers from 1 up to n, you have exactly n integers. So the size of this set is n. Okay, so it's very easy to understand. Now, counting infinite sets is a much more interesting story. I'll tell you on Friday, if you haven't know this. Okay. So today I restrict myself to finite numbers, finite sets. Okay. So now let's do counting. So suppose the two sets A and B are disjoint. That is, the intersection is empty. And then the union, if I count the union, is just adding the size of A with size of B, right? So I suppose A is a set of bananas, B is a set of oranges. Now they are disjoint, so if I count the fruit, so I just add the number of bananas and the number of orange, right? So there's no double counting. Okay. So now in general, this is not the case if you have overlaps. So here is a counting formula for the union of sets. So it has a name called the inclusion and exclusion principle. It's a family of principles. So let's look at the simplest case for two sets. So it says in general, if I count the number of elements in the union, A union B, it is A plus the size of A plus size of B, take away the size of intersection. Right? So from the picture is easy, because if I add everything in the green, so suppose this is the size of A, right? And then I add size of B, so I count the overlapping part twice. So now I take away of this, I get the total number of things in the union. Right? This is fairly straightforward. You can use formulas to say this. So you can argue in this way. We split the union into three disjoint sets, like this part, middle part, left, middle, and right. Now, for disjoint set, we already know that you can just add up the different portion. So the A union B is the sum of the three parts, right? Because they are disjoint. But however, the A is the disjoint union of the first two parts, right? So A is because this is disjoint, so A is A take away B plus A intersect B, right? And B, the same argument goes, B is, the size of B is the same as the number of elements here plus number of elements there. Now if you add these two, and if you add these two, you get this, right? Now, the theorem follows because you can combine. Right. Now this is here with extra copy of A intersect B, so just take away. Right. So anyway, so there's an easy argument to show this is true. Now let's look at an example of applications of this inclusion-exclusion principle. So let's suppose we want to find the number of positive integers which are less than 100, and they are multiples of 3 or multiples of 7. We have to count both, right? Okay. So the answer is a question clear? So we are looking at the numbers less than 100, and somehow they are either multiple of 3 or multiple of 7, right? For example, 6 we have to count, 7 we count, 5 no. Okay. So now we want to count how many elements. So we write them in sets and use inclusion-exclusion principle. So the answer is quite easy. So let A and B be the sets of multiples of 3 and 7, respectively. And then the size of A is just 100 divided by 3, then taking the integer part. So the bracket X stands for the greatest integer less or equal to x. So you just take the floor or whatever. This is, you understand the counting, right? Because you count multiple 3. So every 3 number you have 1. Every 3 number you have 1. So therefore, you have 100 divided by 3, not many. Okay? So you have 33 elements in A. By the same reason, you have 100 divided by 7 taking floor, you get 14 number in B. Now, however, you have to count the intersection. Now, 3 and 7, they are relatively prime. There's no common factor. So the multiples, if you are a multiple 3 and you are multiple 7, you are multiple of 21. So you can count the number in the intersection by using this, right? 100 divided by 21. So you get 4. Now, by inclusion-exclusion principle, the union is the number of elements in A plus number of elements in B, take away the number of elements in the intersection. So you get 43. Okay? So this is easy. Now, how about 3 sets? Okay, so the claim is the union of 3 sets is equal to, you add the number in A and number in B and number in C. You add the number of elements in A and number of elements in B and number of elements in C, but you minus the intersection. And then you have to add back this, the A intersect B intersect C. Okay. So I'll convince you this is true using this Venn diagram. And then I'll skip the derivation part, okay, because of time. So now the left-hand side says I want to count the number in the union. So in this Mickey Mouse shape thing, right? So I want to count this. Okay, now look at right-hand side. What do I have? So I have the red plus blue plus green, right? So this purely red part, I counted once. Okay, so this is all right. The purely blue part, again, I counted once. This is correct. And the purely green part, I also counted once. Okay, right? So these 3 things, if I add them, I count the pure red, pure blue, pure green once. Now, on the other hand, I count the overlapping part. This part, I count twice, right? This part, again, I count twice. This part, I count twice. Now, look at A intersect B. Look at this, for example. This part, I count twice in the sum here. So, zoom into this part. When I count number of elements in A, I counted once. When I count number of elements in B, I counted another time. So I counted twice, right? So now if I add these two but take away A intersect B, I count A intersect B once. So the number is right. Okay? So therefore, if I add these 3, take away A intersect B, A intersect C, A intersect B intersect C, I get everything here correctly, except this part I'm not sure. Okay? Now, for the part in the middle, let's see how many times I counted. Now, inside A, I counted once. Inside B, I counted once. Inside C, I counted once. So I counted 3 times. Okay? When I take away the 3 sets, I take away intersect B, I take away it once. I take away B intersect C, I take it another time. I take away C intersect A, I take it another time. So I did 3 times, take away 3 times. Then I didn't count it, right? So now in order to make my counting correct, I have to add it back, right? So this formula actually counts every part correctly. I don't know whether you, okay, it's quite easy to see it. Now, if you don't believe that, you follow the inclusion-exclusion principle for 2 sets, and just use it over and over again. Okay, so I guess, okay, so, okay, so let's just, there's just 6 lines, so let's go through it. Okay, so I want to use the same principle for 2 sets. I push it to 3 sets, okay? So for the 3 sets, I view it as a union of 2 sets. Okay, I merge A union B as 1 set. Okay, so now by the inclusion-exclusion principle for 2 sets, I get the union of 2 sets is equal to the size of the first set plus the size of the second set minus intersection. Okay, no problem. Now this is a union of 2 sets. I use this principle again. So this guy is the size of A plus size of B minus size of A intersect B. Okay. Now C is here, C is here. The last term we need to take a closer look. Right. So the last term is A union B bracket intersect C. Now there's a law called distributive law for the operation on sets. So by the law, we know that the bracket A union B intersect C is, I can distribute this intersection to A and to B. So this is equal to A intersect C bracket union B intersect C. This is some law of operation on sets. Okay. You can draw a Venn diagram and you believe me. Okay. Now this looks a union again. So the size of the union is the size of first set plus the size of second set and minus away intersection. Okay, so we have first set, second set. Intersection, well, intersect C twice is the same as intersect C once, right? So you get minus A intersect B intersect C. So if you replace the last term with the 3 terms here, because there's a minus sign, all the size of 2 sets intersection become negative. This negative, because of that negative, become positive, right? So we get the formula. Right? Again, it's quite easy to see. Now, example of the principle for 3 sets. Okay, so at Daman High School. So who is from Daman High School? Anybody? Okay, never mind. So, okay, so in that school, we have 55 students, which in either A or B or C, right? Algebra, biology, or chemistry. And the numbers are like this. 28 in A, 30 in B, 24 in C, and 8 in the intersection of A and B, 16 in the intersection of B and C, and 5 in the intersection of A and C, right? Now the question for you is how many students attending all 3 classes? In other words, what is the size of intersection of A, B, and C? A intersect B and C, okay? So now we turn it into a mathematical problem. So let A, B, C denote the set of students taking algebra, biology, and chemistry respectively. And then translate the data. Okay, so I won't do it again. So it's like this. Now, by the inclusion-exclusion principle, you move term around, you get what you want, which is A intersect B intersect C, is equal to the 6 terms. You do plus and minus, right? Now just plug in numbers, you get 2. Okay, so this is, again, if you know what you are doing, it's fairly simple. So this is for 3 sets, 4 sets, 5 sets. Okay, I don't want to do it. In general, you have, it's called inclusion-exclusion, right? So in general, the formula looks like this. So suppose I want to count the number of elements in the union of n sets. Then I should include all the singletons, so I have A1 plus the size of A1 plus size of A2 plus ... plus size of AN. So this is inclusion. And I have to exclude. So I have to exclude all the pairs, the intersection of the pairs. So I'll take away all these AI1 intersect AI2, where I1 is strictly less than I2. Right? So that will give us all possible pairs. Okay? And then you have to include the intersection of triples, then exclude the intersection of quadruples, and then include, exclude, all the way depend on n is even and odd, right? All the way, the last term will be intersection of all of them. Okay. So if you are good at math, you know what mathematical induction is and try it. But in general, it looks like this. Okay, another operation on set is called a power set. I think I'm going to use it once in when I talk about infinity. So let me introduce it. So the power set of a set A, denoted by this curly P bracket A, is the set of all subsets of A. So this so-called power set collects all the X, which is a subset of A. Okay? For example, we know that empty set is a subset of every set. So this empty set appears in any power set. Okay. Also, A itself is a subset of A. So A is also appear in power set of A. Okay. Let's look at an example. Suppose let's look at the set of two elements, 0 and 1. Okay. What is the power set of this S? So we want to get all the subsets of S, right? So let's collect the set based on the number of elements. If the set have no elements, right, empty set, as we know, always in. So the empty set is always there. This is a subset of S, which has no elements. Now let's try the subset of S, which has one element. Okay, so how many subset of S which has exactly one element? Well, only two possibilities. A set has 0, the set has 1. That's all, right? And then let's move on to collect all the subset of S which has 2 elements. Now, that's S itself, right? Now let's move on to collect 3 elements. But S has only 2 elements. We cannot collect 3 elements, right? So no more. So this is a collection of all possible subset of S. So this is the power set of S. Okay? Okay, so now we move on to the last topic on functions. I think this is as a relation. Okay. So function f, we write in this way. F from A to B. Okay. Is a relation between elements in A and elements in B. So somehow it's a relation relating elements. So this F will associate each element small a in A, one and only one element small b in B. It will become clear when I give you examples. Okay. So if F associates B to A, then we write B is F of A. And say that B is the image under F of A. Right? A is called the domain of F. B is called the codomain of A. The set of a subset of codomain, the set small b in B, which was hit by F. So I collect all the small b in B, so that for some small a in big A, Fa is B. So this is called the range of F. Okay, so let's make some remarks about functions. So the important message about function is that it's single value. Here, for each small a in A, we can only associate exactly one number. You cannot have 2. So the important feature of function is so-called single value. Now, why? Suppose in real life I'm interested in multi-value, right? So why can't I study several values at the same time? Well, you can, but it's better that you can decompose multi-value into several single values. So if you understand everything about single value, you understand multi-value, right? So it's no big deal. Our restriction is not too bad and makes things much clearer. So we define function this way. Now, for beginners, you may wonder why. So here, A and B are not too symmetric. The domain is every number in A. But for B, codomain, we may not hit every number. So you may think, why can't we just choose the exact fit, right? Well, in real life, it's not, doesn't make sense because, for example, a typical function is I have a function of t. T is every hour of time, right? Midnight, 1 o'clock, 2 o'clock. So t is my domain. So my domain has 24 hours, 24 hours. Now I want to have a function of at exact hour, I go out and measure the temperature of Singapore. Okay. So I have a function of t, right? So I have 24 data points, and then the value will be the temperature I measure. So this is a function. At every time I have exactly one value. Okay. Now, the codomain is probably from 25 to 35. I think Singapore probably never go down to 25, right? So I can only have a range, have a I don't know what happened, what are the exact temperatures. So I can only give you, how to say, a range, right? So I give you, so the function I'm going to define is from the 24 exact hours to somewhere between 25 degree to 35 degree, right? So it's impossible, I know exactly what I will get, right? So it's reasonable to relax the codomain, and the range is what actually I measured. Right? Anyway, so this is just an explanation. You buy it or you don't buy it, fine. Okay, function has other names called maps, mapping, operation, etc. Okay. Now, there are lots of example functions. So, for example, in calculus or in physics or in engineering, you have seen lots of functions which are often from real number to real number. Okay, so there are linear functions. We have seen this, right? Like this. So ax plus b. And quadratic, the degree 2 polynomials, we see some pictures, parabola, and so on and so forth. And power, so you raise it, so exponential function. Right? Sorry, this is not exponential, but it's some power. And polynomial, which are the sum of this polynomial. And then we have seen exponential, log, sine, cosine, tangent. All these things you've seen in calculus or in, so they are all examples of functions. Okay. You can define function by pieces, right? So the domain, say, you can define function f from R to R by several pieces. If x is bigger than 1, you use this piece. If x is between -1 and 1, you use the other piece. If x is less than -1, you have another piece. It's fine. As long as it's single value, it's okay. Right? Now, very often we, let me show you. Very often we do not look at natural examples. Sometimes we cook some artificial examples to illustrate something. Okay. So for example, we can define a function with some domain and some codomain, whatever we want to do, right? So we choose A to be ABC, B to be 1, 2, 3, 4, and then I define a function f. So from, okay, we define, so we can do whatever we want to do. So we associate A to 2, right? B to 4, C to 2. As long as it's single value, as long as you don't shoot two arrows from the same point, you are a function, right? So for example, this is an example function. This is another example. Right? Okay, now for functions, there are some descriptions. We can look at some functions with special properties. These injective, surjective, bijective is very commonly used. Next time I'll use it to talk about size of infinite set. So it's very important. Okay, so let me remind you, I believe you know this. So let me remind you what is an injective function or one-to-one function. Okay, so function f from A to B is called injective or one-to-one if I send different points to different points. If for every x1, x2 in A, if x1 and x2 are different, the image of them are different. Okay? Or you can say, you can take the control positive in the square bracket. Right? Control positive means P arrow Q. Control positive is not Q arrow not P. Right? So if you don't like these not equal, you take control positive, it becomes, if the image are equal, then the x1 equal x2. Right? If fx1 equal fx2, then x1 equal x2. So these two are equivalent. Okay? But the important thing is distinct points map to distinct points. Okay. Let's look at examples. So for example, I have a function from real number to real number defined by f of x is x squared. So this is not injective because, well, 1 and minus 1 are mapped to same point, 1. Right? 1 square is also minus 1 square. So it's not distinct point to distinct point. But this is this. Now, if you look at cube, it turns out to be different points mapped to different points because this is a strictly increasing function. So you cannot have two different points mapped to the same point. In picture, right? For example, this f, if he sends distinct point A and C to the same point, and then he's not injective, right? Injective means distinct point must send to distinct point, right? So you cannot have two arrows shoot into the same target. If you have two different arrows shooting to the same target, this is a violation of one-to-one or injection. Okay. Now, the other concept is called surjection. So a function f from A to B is called surjective or onto if for every y in B, there is x in A such that fx equal y. In other words, you hit every point in the codomain. Okay. So in other words, range is the same as codomain. Okay. Look at our old friends again. So suppose f is defined by f of x equal x squared. Is this surjective as a function from R to R? No, because anything squared is non-negative. You miss all the negative numbers. So therefore, the function from R to R is not surjective. Now, on the other hand, this cube function, g of x is x to the power of 3 is surjective. You can try to show it because you can take cubic root and then you give you the pre-image. Now we can also use cooked examples, right? So probably I use the picture. Okay, so for example, here I have capital F, capital G. So capital F defined this way. So the domain is ABCD. The range is 1, 2, 3. So I define it like A and B goes to 3, and C goes to 1, D goes to 2. Right? So this is a surjection. This is a surjective function because I hit every point in the codomain, right? Now the G, capital G, this is not surjection because I missed the 2. You see, in the definition of G, I send A, B, C, O to 3, and D to 1. I missed 2. So therefore, this is not a surjection. Okay. So the last concept of today is bijection, which is both injective and surjective. Right? So definition of function f from A to B is called bijective if it is both injective and surjective. Well, the vague idea is a bijection is a perfect matching. Somehow it is also called one-to-one correspondence. So you can match the elements in A and elements in B in a, well, certain nice way, right? For example, we have seen that g of x is x cubed is bijective because we have seen it is both injective and surjective. Okay. Now, using cooked examples, again, let me show you the picture. So the capital F defined here. So here I have A, B, C, D mapped to 1, 2, 3, 4. If F is like this, and this guy is, the capital F is neither injective because A and B shoot to the same 3, nor it is surjective because it missed the 4, right? So this function, no good, right? Now this G, okay, send A to 4, B to 3, C to 1, D to 2. So this G is it injective? Right? No point, no 2 arrows shoot at the same one. So injective. Is this surjective? Is every point here get hit by an arrow? Yes. So this is both injective and surjective. So it's a bijective. Now, what do I mean by perfect matching? So you can think of, right, you can match the elements in in the domain and elements in the range in a sort of unique way. It's not unique. In a nice way, right? So one element only paired with another element, right? No overlap, and you do not miss anybody. So the matching was sort of done in a nice way. Okay. So this is the bijection. So that's all for today. So next time I'll talk about infinity, the infinite set. And there's some, okay, so I need to, okay, so that's the end of the lecture, but there's announcement for something else. Maybe I'll take you another 5 minutes. It's just to help some other classmates. Maybe you should introduce yourself.
Okay, hi everyone, I'm Sing Ching. I'm a Year 4 Environmental Studies student, so I know it's very late, so I won't take very long. So there's a survey link on the screen, so if you can take it down and do it at your own time, it would only take like 10 to 15 minutes. So this will help me in my FYP, and I'm trying to close my data collection by week 5, so it's like 2 more weeks. Yeah, so I'll be grateful if you all do the